Now in my lesson 5, I did look at maybe the factors affecting the electrolysis. I did mention about the nature of electrodes. I did mention about the position in the electrochemical series. And as well, I did mention about concentration. And I actually say that the concentration may affect of course, how it will affect. We discuss about the electrolysis of gray and all that. Now, in my lesson 6, I want to deal with the quantitative aspect of electrolysis. Now, in this I mean here, how we can be able to determine the amount of products formed at the anode and the cathode. Now, it's important that I mention here that according to Faraday's law, the quantity of products formed at the electrode here is directly proportional. It's actually directly proportional to the amount of electricity passed. It's directly proportional to the amount of electricity that is passed through the electrolyte. Now, therefore, it is important maybe to mention here that when you're working out the quantity of products formed at the electrolysis, we need to work out, or we need to know how to work out the amount of electricity. So I'm going to take you maybe how we work out the amount of electricity. Now, quantity of electricity. Now, the SI unit for the quantity of electricity should be coulombs, and the quantity of electricity is also equal to the charge here, and charge here again we can have the symbol for quantity of electricity here is Q, which is also equal to charge, Now, how do we work out the quantity of electricity? Now, the quantity of electricity here will be worked out from current times time here. Now, this current here is supposed to be in amperes. The current is supposed to be in amperes, and time is supposed to be in seconds. Please get note of this because it's very much important here. Especially when it comes to time, because I can use any unit, I can give you a question on hours, minutes. You've got to convert it to seconds. You've got to convert it to seconds. So the current here should be in amperes, and the time should be in seconds. Now, the quantity of electricity that you're going to get from this current times time here, the SI unit for quantity of electricity is actually coulombs. That is what we are talking about. Maybe before we try and work out the product formed at the electrodes here, maybe we can try and look at how we can be able, or an example of finding the quantity of electricity passed. So let's have a question here. Look at that question there. 2 amperes of current was passed through aqueous copper to sulfate using graphite electrodes for 45 minutes. Find the amount of electricity used. So we're going to pass that current through aqueous copper to sulfate electrolyte. We need to find the amount of electricity used. Now, as I just mentioned here, the amount of electricity here, which we are going to use Q here, will be given by the amount of electricity will be given by. Now, the current here, we're going to use the current that should be in amperes. Now, by the way, we're going to use the SI unit here for current will be I. It will be I. Sorry, the symbol for current here will be we are going to use I. This will be the current, this will be the current, and then of course I'm going to use T for time. Now this one here, for the current here, of course, I'm going to have 2 amperes, and then I'm going to try by the time here, and it should be in seconds. Now here I have 45 minutes, so I must convert this minutes to seconds here by multiplying by 60, by multiplying by 60. Now working out this one here, should give you, this one should give you here, should give you 5400 coulombs. 5400 coulombs. So basically that's the way you work it out. Whenever you are given the current, and if it is given in any other form, because it can also be in milliamperes, then you've got to change it into amperes by dividing by 1000. And then of course the time here must always be in seconds. That's what we are talking about. Now suppose in my second question here we try and work out the mass of product. The mass of product formed. The mass of product formed at the cathode. The mass of the product formed at the cathode. Now there are 2 things here that we need to follow to be able to work out the amount of product formed at the cathode. There are 2 important things that we need to have here. One of them is what we just discussed here, that is the amount of electricity. Now number 2 here, we need to have an equation. We need to have an equation for the reaction that actually happens at that electrode, for example, cathode here. Now if you try to look at the cathode here, as we mentioned previously in my lesson 5, aqueous copper 2 sulfate here, we are going to have the copper ions, the sulfate ions, and of course because of water we are going to have hydrogen ions and hydroxide ions. Now at the cathode, I think we said here, between copper and hydrogen ions, as they get to the cathode here, copper ions will be discharged in preference because copper ions have a higher tendency to gain electrons than hydrogen ions. So basically what will happen here, the first thing to do here is to have an equation. Plus 2 electrons here, that gives you copper solid. That's the first thing to do. Now let us discuss something about this equation. Now experiments have been performed on this, and it has actually been noted something have been noted, that when you are discharging monovalent ion, when you are discharging a monovalent ion, for example the silver ion, this one is a monovalent ion with one charge of +1. Now a monovalent ion here requires 1 electron to form the mole of that element. Now experiments have shown here that when you are discharging 1 mole of monovalent ions, you require an amount of electricity equivalent to 96,500. Now this amount of electricity here is what we call a Faraday. So this is 1 Faraday. 1 Faraday therefore is given 96,500. So therefore this is what we're talking about here. That 1 mole of electrons, because this one means that 1 mole of monovalent ion, for example 1 mole of silver ions, we require 1 mole of electrons and we form 1 mole of silver metal. Therefore, forming 1 mole of silver metal, you require 1 mole of electrons, which is actually equivalent to 96,500. And many other experiments, of course, have been made, and this one has been proven. It will not exactly be 96,500, but around there, 96,400, something there. But this is approximately 96,500. Now, to be able to work out this, I want us to think about a divergent ion like this. A divergent ion like this here, which actually requires 2 electrons. It requires 2 electrons for rate. It requires 2 electrons to form 1 mole of copper. Now, in this particular case here, this will mean here that I require 2 moles of electrons. I require 2 moles of electrons to form 1 mole of copper. 1 mole of copper. Now, these 2 moles of electrons here, the 2 moles of electrons here is actually equivalent to 2 Faradays. This is equivalent to 2 Faradays. Very important there, 2 Faradays. And this 2 Faradays here is equivalent to 2 times 96,500. In other words, here, this is what I mean. This is what I mean here. I require, for me to form 1 mole of copper, I require 2 times 96,500 coulombs. Now that means here, of course, you can have it here. If you use this one, you multiply by 2 here, you're going to get 193,000 coulombs. 193,000 coulombs here should give me 1 mole of copper. 1 mole of copper. But now, how much of electricity have I passed? Or have I used? I've used 5,400. 5,400 coulombs here should be able to give me how many moles of copper? Then maybe I can just multiply. I'm going to have 5,400 and divide by 193,000. 193,000. Look at that. Now, working on this one here, you'll get it as how many moles? This 5,400 I divide by 193,000. Now here, working on this one here, I get 0.02798. Look at that. 0.2798 moles of copper. And therefore, to get the mass, of course, when I have the moles, I can have the moles now times the relative atomic mass of copper. And of course, this one is 0.2798. I multiply by 63.5. 63.5 there. And if you work it out here, 63.5, I'll get here 1.77 67 grams of copper. So that's what I'm talking about. In other words, here that means that if you're going to pass a current of 2 amperes for 45 minutes in the aqueous copper 2 sulfate electrolyte, you realize that the mass of the cathode will increase. It's going to increase by 1.7767 grams. That is what we are talking about. Now, in the very same question here, let's also think about the volume of gas produced. The volume of gas produced at the anode. The volume of the gas produced at the anode again as question number 3. So Roman 3 of that. Now, as usual, when you're working out the products here, you've got to think about the equation form. Think about the anode equation. Add the anode here. So this is number 3 here. The volume of gas produced at the anode. So at the anode, of course, we have the sulfate ion and we have hydroxide ions. Very important to note that. And we said here that hydroxide ions have the highest tendency. Hydroxide ions will have the highest tendency. Hydroxide ions will have the highest tendency to lose electrons, and therefore I'm going to have hydroxide ions here losing electrons. And we mentioned here that as hydroxide ions lose electrons, the oxygen atoms and the hydrogen atoms produced here will be able to recombine here, and we're going to have water plus oxygen gas being produced here. Now we mentioned here that when you balance this, you get something like this. You're going to get 4 electrons. 4 electrons. Now, I want us to look at something here. Now, when you discharge 4 moles of hydroxide ions, you get 2 moles of water, 1 mole of oxygen gas. Look at that, 1 mole of oxygen gas, and I'm going to have 4 moles of electrons here. Now, 4 moles of electrons is equivalent to 4 farads. It's important to note that. Now, 4 farads again is equivalent to 4 times 96,500. 500 coulombs. Look at that. 96,500 coulombs. Now, working out this one again here. 96,500. I multiply by 4 here, you get 386,000. 386,000 coulombs. 386,000 coulombs. Now, what does this one mean here? What does this one mean? Let's get now to the calculations here. This one means here that for me to form 1 mole of oxygen, I require this amount of electricity. So this is 1 mole of oxygen gas. Now, therefore, and remember, I have only passed 5,400. So 5,400 coulombs, the amount of electricity that I've just passed here, should give me how many moles of oxygen? This will be 386,000 here. I work it out here, and I want to get 5,400. I will get 0.01399 moles. There's some moles here. Now, of course, if I want to convert moles, given maybe, for example, I'm working with the room temperature and pressure. Now, the molar gas volume at room temperature and pressure is always 24 cubic centimeters. And therefore, if I want to convert this moles to volume, volume at RTP here, I'll just have my 0.01399, and I'm going to multiply by 24. I'm going to multiply by 24. Multiplying by 24 here, I will get 0.3358, and these are cubic decimeter. Those are cubic decimeter. That's what we're talking about. 0.3358 cubic decimeter. So that is basically what we're talking about. Now, so maybe in summary, maybe I can mention a few things. Now, let me give you a summary of what maybe we've mentioned here. And also the calculation part of it. Remember, I've just said here that as far as Faraday is concerned, the amount of substance formed or dissolved in electrons is directly proportional to the amount of electricity that is passed. Now, if we think of maybe of a general equation in the cathode like this one here, I have Mn plus n electrons giving us M. Of course, when I have a charge of N plus, I require n electrons. Now, to get the moles of M formed, I'm going to work from the amount of electricity passed. We can talk of Q, and then I'm going to divide by N. I multiply by F, which are Faradays. So I'm going to take the amount of electricity, I divide by N Faradays, where N is the number of electrons. N is the number of electrons. Fn is the number of electrons. And therefore that means here, this one means that obviously the issue of equation here is very, very, very critical. It's actually very critical. For example, in what we just discussed about, if I talk about this one here, 2 electrons are forming a copper solid. If I want to know the moles of copper, the moles of copper here will be equals to the amount of electricity. This was 5,400. I divide by N, where N is 2 here, so I'm going to have 2 times 96,500. And of course, working out this one here, you're able to get what we had. That's what we're talking about. Now, in our scenario here, when we have something like the hydroxide ions are forming water and oxygen gas, and we say that when you balance this, you get an equation of that form here. Look at that. An equation of that form. Again, here, look at this here. These are 4 electrons. 4 electrons here are forming 1 mole of oxygen gas. 4 electrons here are forming 1 mole of oxygen gas. Therefore, to get the moles of electrons, moles of oxygen gas, the moles of oxygen gas here will again be equals to Q, and our Q here is 5,400. I divide by N. In this particular case, the number of electrons here we require is 4 electrons. Therefore, I'm going to have 4. I multiply by 96,500, and this is what we've just talked about. So basically, that is all that you need. Kindly remember, Two things. Two things. One of them, the formula for getting amount of electricity. Amount of electricity, very, very important. This is current times time. The current should be in amperes, and the time should be in seconds. Number two, the cathode equation and the anode equation. Very, very, very much important. If you don't know what will be formed at the cathode and anode, or you don't know how to write this equation, then automatically you'll not be able to get the amount of the product formed. So basically that's what I'm talking about. Now let me take you through the applications of electrolyzers. Number one, I'm going to discuss electroplating. I'm also going to discuss the purification of metals, and maybe of course I can mention also about the other applications, like the manufacture of pure chemicals like sodium hydroxide and so on and so forth. Now let me discuss maybe a few things about maybe electroplating. Now when electroplating here is basically coating of a metal with another using electrolysis. Now electroplating is done, number one, to prevent things like corrosion. For example, we know that something like iron can rust. It can rust if exposed to water and air. Therefore, maybe to prevent this rusting, you've got to coat it with another metal that cannot rust. Something, for example, like silver, the chromium, and so on and so forth. Then, so how do we do it? How do we electroplate a substance? I want us to think about how we can be able to electroplate, for example, a spoon, and I want us to use the silver. I want us to electroplate a spoon using silver. Now, how do you go about it? Now, when you're given maybe a question like to draw a diagram that may be used to electroplate a spoon using silver, then what you're going to have, one, the consideration that you're going to make. Number one, your spoon will have to be the cathode. Your spoon will have to be the cathode. Why should it be the cathode? Because we know that the cathode actually attracts the positive ions. It attracts the positive ions, and when the positive ions get there, they will be able to gain electrons and will form a metal on the surface. And basically that's what the electroplating will be about. So the electron here, I'm going to have my, whatever I'm electroplating, this is a spoon. The cathode here, we are going to have the spoon that is being electroplated. Now, remember here I'm electroplating using silver. Now, when I'm electroplating using silver, I've got to use the silver anode. Look at that. I'm going to use the silver anode. Please get note of that. A silver anode. That's what I'm going to have there. Now, again here, if I'm going to use, if I'm electroplating using silver, then even the electrolyte should have silver ions, and therefore here you can have something like silver nitrate. Silver nitrate, that's what we're talking about. I repeat again, whenever you're electroplating something here, the substance to be electroplated is always put or connected to the negative terminal. In other words, it acts as the cathode. The substance, for example, the substance that is electroplating there, that's for example the silver, should be the anode, Maybe I can mention about a few things about basically what happens, because this one here is there's a chemical reactions happening. I can mention about what really happens at the cathode. Look at that, what happens at the cathode. Now at the cathode, what happens here, in my silver nitrate solution, of course, I have the silver ions, I have the nitrate ions, and of course because of water I'm going to have hydrogen ions and hydroxide ions. Now when silver ions and hydrogen ions, of course, this one will be attracted to the cathode. Now when they get to the cathode here, silver ions have the highest tendency, look at that. Silver ions have the highest tendency to gain electrons, and therefore will gain electrons and form silver metal, and therefore the silver metal now will be able to form on the surface of my spoon. Now what happens at the anode? What happens at the anode? Now when I was discussing about the factors affecting the electrolysis, I did mention about the nature of electrolyte. And when you say that here, every time you use a metal and then more so at the anode, what will happen is that because metals have higher tendency of losing electrons, they have higher tendency of losing electrons here than this anion. So what will happen here, the anode, the silver will lose electrons. The silver will lose electrons. And as it loses electrons here, it will actually form silver ions. It will form silver ions plus an electron. Now what will be happening here is that when the silver ions are released now, they are released into the solution, and once they are released into the solution, then they get to the cathode where they gain electrons and form the silver solid. That is what we're talking about. And therefore this one just summarizes what really happens in the during electroplating. Now once again, I've just mentioned here, now electroplating is done for two things. Number one, to make a substance, to improve the appearance of a substance. For example, in this spoon here, you electroplate with maybe an appealing color. For example, silver is silvery there. I can just electroplate. If I want to prevent corrosion, I can also electroplate. Those are two things that I can be able to do. Now, so then let me discuss the second. Application here. The second application here, and this one is the purification of metals. The purification of metals. Number two, purification of metals. Now, purification of metals. For example, e.g. copper. Let's look at that. E.g. copper. Yeah. E.g. copper metal. Now, how do I purify? If I have an impure metal. And it's important maybe to know to mark this one here, because we also use this when we are discussing the extraction of metals. And this one actually forms the final stage in the extraction of metals. Now, when I'm doing or when I'm purifying metals, all I need to do here, I need to have look at this here. This is electrolysis here. Now, if I am purifying copper, now these are the few considerations that I need to have. The impure copper here is put at the anode. This is impure copper anode. Please get note of that again. With the very same reason that we've discussed here, that if you happen to use a metal as the anode, what happens? Instead of hydroxide ion being discharged here, that metal will lose electrons here and will dissolve. It is actually going to dissolve. Now, what are we going to have at the cathode? At the cathode here, I can have, for example, pure copper. I'm going to have pure copper. I'm going to have the pure copper. We're using pure copper so that maybe the copper ions that get to the cathode there, again, are going to gain electrons and are going to form copper metal, and that copper metal actually forms on the surface of it. That's what we are talking about. So again, maybe we can also be able maybe to mention about the equations or the reaction that happens at these electrons here. I can mention about the cathode, for instance. What happens at the cathode? Now at the cathode here, before we get to the cathode, I'm going to use a solution containing copper ions. I'm going to have a solution containing copper ions. In other words, I can use copper 2 sulfate. I can use copper 2 sulfate. I can use copper 2 sulfate. I can use copper 2 sulfate here. Now, this is kind of the setup that I'm going to have here. I'm purifying copper. I need to have an electrolyte containing copper ions. For example, I can use copper 2 sulfate. The anode will be the impure copper. The cathode will be pure copper. That's what we're talking about. Now, what will happen here? Now, so what we're going to have here with these ions here, the copper 2 sulfate, of course, I'm going to have the copper ions, and I'm going to have hydrogen ions as the only cations there. Now, when the copper ions and the hydrogen ions get to the cathode, obviously what will happen here is that the copper ions with higher tendency to gain electrons will obviously gain electrons and will form the copper solid. Will form the copper solid. So what are we going to have here? The mass of copper. The mass of copper will increase. We are going to see that the cathode or the pure copper there increasing in mass. Let's have a look at maybe something of what happens at the anode. Now at the anode here, what will happen? Instead of hydroxide ions, losing electrons to form oxygen and water, as we noted, what will be happening here is that copper will be dissolving. Copper will be dissolving because copper can easily lose electrons than the hydroxide ions. Therefore, copper will lose electrons and will be forming the copper ions, and of course releasing 2 electrons. Now, the observation that we make for this obviously is that the copper will be seen to dissolve. The copper will be dissolving, and as it dissolves, it actually releases the copper ions, and then copper ions will be attracted to the cathode, where again they go there, they gain electrons and form the copper solid. So basically, this is what we're talking about. In a nutshell, at the anode, the impure copper dissolves. At the cathode, so what will be in the cathode there? Mass will be increasing. The mass will be increasing. That's what we are talking about. So kindly let us get note of this. You can actually get a question on this here. You draw a setup that can be used to purify copper metal or any other metal. What you just need to note there, the impure form will be at the anode, the pure form at the cathode, and of course the electrolyte must have the ions of the metal that you are purifying. That's what we're talking about. Now with the application, that one maybe I've not mentioned about it so much, but of course we have it. We can talk about the mercury cell that we use in manufacture of sodium hydroxide. We do have the production of other chemicals, like for example chlorine. We can have it from electrolysis of something like brine and so on and so forth. And basically this marks the end of my lesson 6, and I think maybe this could be the end of my discussion on this topic. If maybe you have any queries or so, maybe you can have it on my on my page, page there, and I think we'll be able to handle it. So thank you very much for this. Kindly share, like, subscribe, and leave a comment, and I will be grateful. Thank you very much, and God bless.